Hi there, my name is Aaron Lanterman. I'm a professor of electrical and computer engineering at Georgia Tech, and this is my quarantine hair. And I would like to welcome you to the fifth lecture in the summer 2020 offering of GPU programming for video games. In the last lecture, we talked about orthographic projection, and in this lecture, we'll talk about perspective projection. In orthographic projection, objects would appear the same size regardless of the distance from the camera. With perspective projection, things that are closer to you are going to look bigger than things that are further away from you. All of the projection transformations we're looking at this point have assumed that we've gone through the view transformation, and so we essentially have a camera that is looking down the z-axis with everything centered. And then at that point, the orthographic projection would take a three-dimensional volume defined in that view space, aka camera space, aka eye space, and transform that into a normalized 3D volume in clip space. A projective transformation is quite different. Here we're basically taking this kind of trapezoidal shape. It's like a giant pyramid with the top chopped off here at the near plane. And this is called a frustum. And what we're going to do is take this and project it into a rectangular volume. Now, we're inherently outside of the realm of linear transformations at this point. This is going to require new math in order to do this kind of transformation. You can imagine that you see a bunch of objects outside, and essentially you're in a dark room looking out at the things outside. You could imagine that this window is the near plane that things are going to be projected onto. So with both orthographic and perspective projection, choosing the near and the far plane has a few practical impacts. One is anything beyond the far plane is going to not be seen. And you can get problems if you have something in between where maybe you're going towards a particular object, and then when the far plane connects with the object, that object will suddenly pop into view. If you've played 007 GoldenEye on the Nintendo 64, you've probably seen a similar problem with the near plane where if you sneak up behind a guard and you get close enough, the near plane will sort of chop off the back of the guard's head and you can see the back of their face, which is fairly weird. In case of things popping in and out of view in the back in this far plane, sometimes people will add a fog effect to try to obscure that, but it's still a thing that will happen. Also, choosing the near and the far plane is important from a practical issue in both orthographic and perspective projection, because the Z information is used to determine which objects are closer than other objects, in particular, which objects are obscuring other objects. And if you set your near and far plane too far apart, you may not have enough resolution in Z to resolve that well, and you can get this strange shimmering effect called Z fighting. So we're going to take this particular frustum, this chopped off pyramid, this trapezoidal looking pyramid thing. We're going to map this thing that is inherently not a 3D rectangular volume into a 3D rectangular volume. So the left bottom and near and the right top and near coordinates, these are meaningful in this window that we're going to be projecting our 3D space here onto. Notice up here I'm just writing Z equals the far plane, because the right and top and left bottom coordinates out here, the one over here isn't going to be right and top. It's going to be something else depending on the various angles here. Now, I've drawn this according to the direct 3D convention. If this was OpenGL, this lower left corner here would actually have a -1 in that spot. The matrices I'm going to show you in this derivation are D3D style, but you can change the derivation a bit and get this OpenGL style if you needed to derive that for some reason. So we're going to take objects in this space and project them onto this near plane. And once they're on the near plane, we'll map left to right to -1 to 1 and bottom to top to -1 to 1, just as we did with orthographic projection. But remember, that only applies now once we're on the near plane. This sort of applied throughout the entire 3D volume with an orthographic projection, but this is going to be fundamentally different. Okay, so let's talk a little bit about the mathematics of this transformation. So we have a point, say it's XYZ in our 3D space, and we've determined that it's in the volume that we want to transform. we want all of the points in our space to be going through a point at the origin at 0, 0, 0 here. Again, we've assumed that the camera has moved into this point. We're going to basically take all of our points in space and run them along lines that go through this point. And what we want to do is see where they intersect the near plane. So the basic idea here is that everything needs to make similar triangles. All of the angles need to match up. So for instance, if I take the ratio of a point on the near plane, my new x-coordinate, which I'll call here x double prime, if I take the ratio of that x double prime to the original x, that needs to be equal to the ratio of my near plane z-coordinate to the actual z-coordinate that I'm transforming. And if I rearrange that a bit, I can get an expression for that new x double prime in terms of the x that I'm transforming, the near plane, and notice the z-coordinate. So this transformation is inherently nonlinear, and this is something new. We'll have to handle that carefully. What we want to do is try to keep as much of the calculation as we can in that linear matrix algebra space so we can combine it with other matrix stuff that we're doing. But there is a point where we are going to have to do a division operation that you can't do with just a straight matrix multiplication. Now, the similar triangles we're making have to work in all of the coordinates. So for instance, the ratio of y double prime to x double prime should match the ratio of y to x. And so I can manipulate that to get a similar expression as what I have up here. Or you could just kind of do this logic directly and get this expression for y double prime in terms of ny divided by z, just as we had up here for x double prime. So once we've done that transformation, we now have an x double prime that should be living in the space of our left limit to our right limit, and our y double prime is in our space going from the bottom coordinate to the top coordinate. At that point, we can use the same formulas for orthographic projection that we derived in the last lecture to map these into a -1 to +1 clip space. And so we can do that here. So what we've got here is our x prime basically, and what we have here is our y prime. Again, I should give credit to this amazing article by Joe Farrell that I think it's 2 R's, 2 L's, that most of this discussion is based on. He uses a slightly different notation. He uses an x prime here. I wanted to use this x double prime to make certain distinctions a little clearer. Anyway, so, this isn't x prime, this is x double prime, and that's y double prime. That's the point. What we have here is something that starts to look like the kinds of transformations we've done before, and it feels good, except there is the z here. That's not something we can represent with a matrix. But if we multiply everything through by z and just say, okay, well, we're not going to be dealing with x prime and y prime. What we're going to have here is x prime times z and y prime times z. We're just going to say everything's going to have z in it, and we'll get rid of that z later. Because then I can express that as a thing that has an x and a z, and a y and a z, and I can express this as a matrix computation. Now we'll need to think a bit about what we want to do with z prime. So we figured out how to transform x and y. We do need to do something with z because that's going to have some depth information in it. We're going to need to figure out obscuration. So let's keep things consistent. We're going to take z and we're going to map it to a new z prime times z and try to figure out something here that makes sense. So what we're going to do is suppose that our near plane is going to map to 0, a z prime of 0. Z equals f, our far plane is going to map to z prime equals 1. If I wanted to use an OpenGL convention, I could have z prime equal -1, but here we're doing the direct 3D convention. And so if I want to do that kind of mapping, I know what I can put in up here. So if I want the near plane here to map to 0, I can plug that in and get this first equation here. And now if I switch color, let's look for the other situation. So if I want to plug f in for z, I'm going to want a 1 out for z prime. And so if I do that, I wind up with this expression. I could redo these expressions if I want for the z prime equals -1 and run through the same kind of logic if we need to, but we don't really need to do that right now. I have two equations and two unknowns. It's easy enough to solve those and find out what the p and q are that I need. I can write out the full expression just by taking that p and q and plugging them in. And then I have another formula like what I've had before, where we're mapping everything to something that has a z in it. Now, if I combine those three expressions from the previous slides, I get this. I'll explain in a second why I have this w prime times z there. So I'm going to put everything into a matrix. So I'm going to map an x, y, and z into an x prime z, y prime z, and a z prime z. That's all well and good. And so that's being handled by these various things here. And now I've got a question of, well, what do I really want to do with this w prime coordinate? So the convention is that we want to eventually divide everything by z, right? We want to get rid of this z, this z, this z, and this z. So the way that's typically handled is that we'll basically take this fourth coordinate, which should be consistent, is w prime z, and we'll stick z there. And then somewhere on the card, we'll have a piece of hardware that basically takes everything in this vector and divides it by that fourth coordinate. So what we're going to do is we're taking that third coordinate, that z, and we're sticking it in that fourth coordinate. And that's what this 1 here does. It takes that z and puts it in this fourth w coordinate. So now when I divide everything by this omega prime z, I'm dividing everything by z. Doop, 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 doop. And then I'm left with my x prime, my y prime, and my z prime. And then I'll be left with a 1 in that w coordinate. So just as we saw with orthogonal projection, rarely do I need the full flexibility of having a separate L and R and T and B. Usually I can assume that there's some symmetry going on, so I could just define a width and a height instead of having an L and R and a T and B, in which case the matrix on the last slide simplifies in the way you expect. But even then, expressing things in terms of W and H is usually not how these kind of matrices are expressed. Usually there's a field of view that's expressed in either radians or degrees, usually degrees from the point of view of, say, your level designer who's deciding how to set up the camera. This field of view is defined in this vertical direction here, and then there's an aspect ratio that you define in order to define the width. I'm mastering this presentation in a 16:9 aspect ratio. That's probably what you're viewing it on YouTube. The older standard definition video typically had a 4:3 aspect ratio. This is sort of an original television type of standard. This is a widescreen kind of standard that all modern monitors and laptops support, basically for watching movies. And then, of course, we'll also need to define our near and far planes. There's some trigonometry involved in figuring out how the field of view maps into that height and the width. I'm not going to bother going through all the trigonometry. You can dig into that if you want, but we can take it on faith for now. Not surprisingly, there are commands built into 3D APIs to create these matrices for you. Direct3D and Unity both have a left-handed system by default. The Direct3D version, as we mentioned last time, because Direct3D has a C basis, you need to pass in a pointer to the matrix data. But something like Unity doesn't really need that. You can create a matrix and then return it without having to pass around pointers explicitly. Unity has a 4x4 matrix library specifically with some matrix creation routines like this. There is, of course, a right-handed version of this in some APIs. Again, this is a little bit strange because the underlying math here would work for a right-handed system. You just put in negative numbers for f and n instead of positive numbers for f and n. But even though the far plane and near plane in a right-handed system should be defined with negative coordinates, all of the APIs assume that you are passing in positive numbers. So that's why you see the n minus f here looking different than you see in the f minus n here on the previous slide. It's just doing that negation for you. So that's built in Direct3D. XNA has its own version of it. And OpenGL has a version for it because OpenGL is naturally right-handed. And here, this has a C basis, but as I mentioned last time, OpenGL has a stack computation model. So this is pushed onto a stack to be used later. So even in the C context, you don't need to specify a pointer. You can create your own projection matrices in Unity using either the kinds of routines we've talked about, or you could write something that does some sort of really weird bespoke matrix. Your camera has an instant variable projection matrix that you can assign that to. But you really only need to do that if you're doing something fairly strange. So the documentation mentions oblique projection, which is a weird non-standard projection outside of what we've looked at. And it's apparently used by the water rendering system. And again, you'd only really need to do something like this if you're doing something particularly weird. Unity will take the various parameters of your camera and create these matrices for you as needed, depending on how you set things in the inspector. And you can also change those things via script if you've got a reason to do that. So there is one final transformation, and that's where this -1 to 1 gets mapped into the actual pixel count on your screen, the integers. So in doing 3D graphics with modern hardware, it takes a while to get used to that if you're used to doing 2D graphics programming where you're using integers to explicitly index certain pixels. But of course, this does eventually happen. You probably have something else in your operating system and API that you're calling that's defining where various windows are in your screen in terms of pixels that are then taking these -1 and 1 and mapping them to various places. And as we'll see later, it can be even more complicated because you might be doing anti-aliasing where you're actually rendering into a buffer that has denser pixels than you're actually displaying. And nowadays, a lot of this is just handled behind the scenes for you. So essentially, we'll leave that to the magic happening in the API and the card for now. Unity defines several coordinate conventions. Again, these are Unity specific. If you're using some other engine, there may be a different set of nomenclature. It defines a viewport system that has 0, 0 here on the bottom left and 1, 1 on the upper right. The viewport system doesn't have any sense of a z-coordinate. Now, there are also screen space coordinates that go from 0, 0, bottom left, into something that's more of an integer pixel thing. So we have a pixel width and pixel height. And then there's also, in this setup, there is a z-coordinate, and this is in quote-unquote world unit coordinates from the camera. So notice that these have different units. So for coordinates for Unity's built-in graphical user interface facilities, 0, 0 is now in the upper left. You've got these camera pixel coordinates now in the bottom right. So the first two here are closer to the kinds of conventions we've been looking at so far in terms of how you map 2D coordinates, where the y-coordinate increasing means you're going up the screen, whereas this GUI coordinate space down here, this is closer to traditional 2D graphics programming where increasing y-coordinates are going down the screen. All right, so if you are not taking GPU programming for video games in the summer 2020 semester, you can check out now. But if you are taking GPU programming for video games in the summer 2020 semester, I would like you to do the following. So by the time you see this, I will have set up the Piazza website for this course, and I'm going to make a post that says something like answer for lecture 5 task or something along those lines. I want you to find that post and make a response. And I would like 2 things from you. I would like you to take the first letter of your last name, and I would like you to turn that into a numeric value the usual way. So I would like you to map A to 1 and Z to 26. So you're taking a letter and turning it into a number. And then I would like you to take that number and I would like you to square it. Yes, you may use a calculator. So take that number, square it. And that's the first thing I want you to do. That way I know that you've watched this video. For the second thing, I want to know, where are you? So where are you living now? Where are you currently dealing with this distance learning situation and difficulties? Just because I'm curious. Now, there is another option. If you, for privacy reasons, don't want to say where you are on Piazza because other students will be able to read this, you can email me this information. If you do so, put GPU, let's say, lecture 5 task into the subject, and then I can find it quickly, easily when I'm searching. Tell me the same things, but this way you can keep your location private if you've got a good reason to do that. And a good reason to do that is because you want to do it. So, but if you are willing to let your classmates know where you're at, I think it would create a bit of camaraderie if we sort of have a sense of where each other are, and that gives you sort of philosophically a better sense of where you are. Take the sentences I just said and rearrange them until they actually sound profound and useful.